Und ja, jetzt muss ich noch mal kurz einstellen. Ja. Warum diese Taskleiste mich immer ärgert, weiß ich auch nicht. Okay. Wir hatten angefangen mit Markov-Prozessen und diese Markov-Prozesse beschreiben immer den Zustand, wenn wir einen Übergang haben von einem Zustand zu einem anderen Zustand oder vielleicht zu einem dritten Zustand haben oder eine Rückführung in einen früheren Zustand. Dieses Rückführen in den früheren Zustand kann jetzt zum Beispiel sein, eine Reparatur oder wenn wir kein Failure haben, sondern ein Fault, also wir machen ein Reset, wir bringen das Ganze logisch in den funktionierenden Zustand. Und das Wesentliche ist, dieser Markov-Graph, der macht also jeweils einen Kreis für die Zustände und wir zeichnen Übergänge ein als so gebogene Pfeile und an diese Pfeile schreiben wir die Übergangswahrscheinlichkeiten von dem einen Zustand zu dem nächsten. Also das wäre jetzt P12, wäre jetzt die Übergangswahrscheinlichkeit. Wir wollen aber auch die Übergangswahrscheinlichkeit haben in den Zustand, in dem das Ganze ist. Also die Wahrscheinlichkeit, mit der das in dem Zustand bleibt. Und deshalb ist das dann hier P11. P12 hatten wir hier gesagt, das waren ein Element und ein redundantes Element. Die haben also dann die Ausfallrate Lambda plus Lambda r dt. Wiederum nur so zu nehmen im Bereich kleiner Zeiten. Und gleichzeitig haben wir hier die Wahrscheinlichkeit, dass es bleibt in dem Zustand. Das ist dann eben 1 minus Lambda plus Lambda r, Klammer zu, dt. Wenn wir im Zustand 2 sind, dann können wir definieren, dass wir vom Zustand 2 auf den Zustand 1 reparieren. Wir könnten aber auch was anderes definieren. Das ist wiederum sozusagen die Aufgabenstellung oder den Fall, den wir repräsentieren wollen. Wir könnten zum Beispiel sagen, vom Zustand 2 gibt es keine direkte Reparatur, sondern wir wollen immer erst im Zustand 3 sein. Ja? Sorry. Yeah. Yes, we had started in German, so yes, of course. When we are in state 2, Z2, we can go back, but we could otherwise define also that we do not go back, then there would be no transition P21. For instance, by definition, P21 can be 0. In that case, there is no direct transition. For instance, if from Z3 there would be no way back, then that would be an absorbing state. So here we have P32, here we have P23, here we have P33, and in that way we can define the transitions. Then what we can do is we can just multiply the initial vector of states with this matrix of transitions. So in that case, how many would it be? It would be 9. So 1, 2, 3, 4, 5. Is it correct? P2, 2. 1, 2, 3, 4, 5, 6, 7. What did I forget? Okay, we must, in fact, we must have a 3 by 3 matrix. Why don't we have it? Yeah, of course. P13 is 0, so we didn't put it in, and P31 is also 0, so that could be a transition. And back. But it is not there. But in fact, if we have 3 states, we must have a transition matrix of 3 by 3. Okay. That is, let's say, the simple method. Just form the transitions, P12, multiply it and do it iteratively for each time step. Again, there was a question whether how to select the time step. If we do it numerically, for instance, in Excel, and my idea is that the time step is small, maybe 1% or so of mean time to failure, or even lower. So take many steps, and in that case, we can get it correctly. If the time step is too big, again, it can happen that some probabilities are above 1 or in the region of 1 where they shouldn't be. And in that way, having too large time steps from in each iteration, you get a wrong result. Okay. But now let's go for the exercise. And before we do that, I would also like to show you the accurate method. So we can, for that development of Markov processes, where I made previously the approach with Markov chains, but with very small steps. We can make a transition to Markov processes, and in that case we write a differential equation, and that says the vector pj of t and the change of that per time is minus some sum of all transitions from 1 to m ej times the vector at that time plus the sum of all vectors pi, again multiplied with that matrix. And in that way, we can make a differential equation, and that can be, for instance, integrated, and in that way we can solve it numerically, but numerical solution is only sensible for simple cases. Okay, now let's proceed, and maybe it's better to make an example here. And also to exercise it. In our case, we would have two equal sensors, element 1 and element 2, and each has a failure rate of 10 to the power of -4 per hour. What is that? 100,000 fit. And these are switched in parallel, and we have a third element which has somewhat higher failure rate, which is 2 times 10 to the power of -4 per hour. That is in series with these, and in the case of any failure, the system is repaired, and the repair rate is 10 to the power of -2 per hour. That means we have 100 hours repair time or mean time to repair, and we regard a total time of 100,000 hours. First of all, we draw the reliability block diagram. Then we have to draw the Markov diagram with all the states and the transition probabilities. Then we calculate the availability for the system. We calculate the functional reliability of the system. And we calculate the functional reliability for the system when there would be no repair. We draw the Markov diagram with the states and the transition probabilities. Also in the case when the system is repaired only in the case of a system failure. So the difference is, for the first question, in case of any failure repair, and in the second case only when there's a system breakdown, we will do that. Okay, so first of all, we do the reliability block diagram. That's not a big effort. We can see it here. Okay. E1, E2, E3. How many states do we have here? Can you give me a value?
It could be 8.
Yes, but we could reduce it. So we could say the case 1 is failed and 1 and 2 is functional, and at the same time, or in another case, 1 is functional and 2 is failed are equivalent. That would be applicable in the case of hot redundancy. Yeah. And so in that case, we could say we can reduce to 6 cases. Yeah. Because each of these combined cases can be combined with E3 is functional or E3 is not functional. So we can say for the first case would be E1 is functional. The second case would be combined with this. The third case would be both are not functional combined with this. And then we have the complementary case. Okay. System. Here the system is up. Here the system is up. Here the system is down. Here, and in all of these cases the system is down. Can we compute the probability of each state? Yes, the probability here is that that happens, and that happens, and that happens. So that is a R1, R2, R3. The probability that that happens, and that happens, and that happens is R1. Yes. F, so it doesn't make a difference, F1 or F2 R3, and that must be twice the case. And here we have the case F1, okay, times F2 times R3. And here we have the case R1, R2, F3. And here we have the case 2 times R1, F1. That's because R1 is R2, so they are equivalent, times F3, and here that's F1, F2, F3. That's the probabilities. Now we have to make the Markov graph. So we start from Z1, all is functional, and we go to the next state, Z2, where one of these is failed. What is transition probability here. How much is it?
1/2 times delta t?
Yes, not precisely, but it is 2 lambda. Okay, we can say lambda 2, it's dt. Yeah? So, there is no way back because we say, there is a way back because we say, in the case of any failure repair, and P21 is mu dt. So what can happen then? We can go to state 3, for instance. The other element also will fail, and now we have here lambda 2 dt. That's the P23. Where do we go back? We repair, and what does it mean? We repair. In that case here, we have 1 failed. In that case here, which is not very probable, we have 2 failed. And the question would be, would we repair only to the previous state and wait 4 days? And so we would say, no, we wouldn't do it. Maybe we go back to the completely repaired state. And again, P31 is mu dt. Okay, then of course here 1 has failed. We can also go to we can come to state 4. That is, the third element will fail. And that is lambda 3 dt. That is P14 is that. Again, we repair back. Okay, so here we can come to state 5. So here that means the third element is failed, but in addition, one of the other can fail again, and so set 4, 5. No. P45, I wanted to say. It's again 2 lambda 2 dt because any of these 2 can fail. Again, here we can say P51 is again mu dt. And of course we have state Z6 where all is failed. So we can go from 3 to state 6, or we can go from state 5 to 6. So here it's lambda 3 dt, and here that, what is it, Z5? Oh, just a second. Z3? Yeah, from 3 to 6, that is failing. From 5, yeah. And here again, P61 is okay. That would be our Markov graph in case we repair always to the initial state. So in fact, now we have how many transitions have we defined? So here we already have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we have 6 remaining. And that means that would be, I hope I'm correct here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, was it correct? 19 are non-existent. So by definition, Pej for these 19, it's 0. And in that way, we can build up our matrix. And so we can say we have done this. We have all the transition probabilities. What I will not do for all cases, but only for some cases, is the question of P55. For instance, it is 1 minus, and now we only take the one going away, mu plus lambda 2 times dt. So here we always take the complementary to the probabilities going away. And in that way, we can do that for all cases here. For instance, here, I just do it again. P22 is 1 minus mu plus lambda 2 dt. And in that case, we can build up a transition matrix. And again, we can do it, for instance, in Excel. And in that way, we can increment from step to step, always by this multiplication. And in that way, we can get the evolution of every state, Z1, Z2, Z3, Z4, Z5, Z6. And so we get the probability of being in a certain state after that time. Please note that in that case, it is the availability we have computed. We can also compute a reliability in the case of repairable systems. In that case, we do not add up all of the probabilities in the case of a functional system, but we add up only the probabilities or the transitions in the case where the system was in a functional state previously. So you could say a system which is repairable is only reliable when you start from a functional state. And that can be also implemented into that Markov graph. Okay, now let's go ahead, calculate the availability for the system, calculate the functional reliability for the system. So, okay, that both we have to do in Excel. And we calculate the functional reliability for the system without repair. How can we do that? That again is simple. We take these two cases. Only in these cases the system is functional. So RS is R1, R2, R3 plus 2 times R1, 1 minus R1, R3. And in that way, we get the reliability. The failure function of the system is either 1 minus RS or it is F1, F2, R3 plus so I have put that just separately here. And so both must be complementary, and in that way you can compare whether you have computed the correct values. Okay, in that way we have done that. And of course, if we take the transition probabilities, in the case the system is repaired only for a system failure, and that means we do not repair from state 2. And that would mean when we delete this, that would be the second part of our solution. Okay, and in that way, we have investigated this. Some time ago, I had a student and I supervised her in a quite complex system. So we wanted to know what is the probability of a severe accident in case, for instance, some autonomous driving function will fail. That was interesting work, but it also showed us that it is very hard to solve numerically cases where, for instance, we have 1,000 different states, which can easily be achieved in a realistic technical system. Because in such a system, we have 1,000 states, and how many transitions do we have? We have 1 million transitions. And what we must investigate is, for each state in which the system is, for all 1,000 states, we must decide, is the system functional or not? That's one thing which is relatively hard, but which can be achieved using reliability block diagram and some autonomous searching function. But how to implement 1 million transition rates or transition probabilities, and how to get these data. And now imagine you would have to do this by hand, and that is in fact a limit of the method. I don't think the real limit is the computer power, but the real limit is to put in representative data into the computer. Yes, how do you get 1 million transition probabilities? Because these must be reasonable in a physical way, and these must be selected. And here in a complex system, that is hardly possible. So that's one of the limits of the methods. But I think there should be sufficient room for research in that field. Okay, so we can see how we can use Markov processes. I think I uploaded the Excel sheets onto the Ilias, and there you can try. I also think I had both solutions, and so you can either build your own Excel sheet or you can play around with my prefabricated solutions. Okay. Now let's go to number 8. And now we are dealing with software dependability. So where is it? Yeah. Okay. Software is an important part of all systems that must be safe. And for instance, for software, also an FMEA can be performed in order to find out what can go wrong here. But in our case, I would like to start first with something remarkable. So if we have a complex system, for instance, let's say the telephone system in a state, of course, in fact, nowadays it doesn't exist anymore really, but it's more the internet which is used to transport telephone information. But some decades ago, this was really a hardware system, mainly using relays and some, let's say, analog amplifiers. And at that time, there was already roughly 20% of software and 80% of hardware, which constituted the value of such systems. By the year 2000, maybe 80% of such systems are constituted by software and 20% by hardware. So in fact, many of the companies doing telecommunications, they just vanished because until the 1990s, it was their business to sell very expensive hardware, but nowadays mostly software defines the functionality. Okay, and of course in many systems the software can be just copied, and in that way it is much cheaper than copying hardware or than doing hardware thousands of times. Okay, that was some information I got from a textbook and also by a company who was still in existence at that time, maybe 20 years ago. In fact, they also vanished from the market. And software can be very crucial because when the software breaks down, we can have a total system breakdown. And on the other hand, there are some remarkable examples. When you go to that homepage, it is many old examples. For instance, one time ago, Ariadne rocket, in order to shoot up satellites into space, it was lost just because of a very simple software failure. So in fact, the precision of computation was not enough, and that led to the fact that there were two redundant sensors, and these sensors had different output, and so the system decided to destroy the complete rocket before it could make more damage. In fact, that rocket fell into the Atlantic Ocean, and in that way $100 million were lost. Okay, something which is even worse is when the health or the life of people is endangered. For instance, what is important when we have linear particle accelerators that are accelerators which create something like very hard X-ray radiation or gamma radiation or beta radiation, and in that way we can target this radiation at a tumor, and the tumor can be destroyed in that way. And so here there were some such accelerators constructed. The initial was the TERAC 25, and that TERAC led to overdosing of 6 persons in North America. And now if you have a radiation burn, that's something which is extremely painful, and in fact it's really cruel, and people will perish, and in that way it is something which must be avoided under any circumstances. In fact, there had been 2 previous accelerators, one the TERAC 6 with 6 mega electron volt particle energy, the TERAC 20 with 20 mega electron volt particle energy. Now, these accelerators have different modes of operation. As I said, they can use beta radiation, which is electrons, or you can have gamma radiation, which is something like X-ray. And the initial versions, like the TERAC 6 and TERAC 20, they were hardware safeguarded. That means, for instance, to give you an example, there's a treatment room where the patient is, but no other person may enter here because the radiation is really dangerous to your health. And in that way, when someone is under radiation and someone else would open the door, the system would shut down, just to give you an example. There are other safeguards. For instance, if you are in gamma mode, you must have another power level than in beta mode, and in that way, that all was safeguarded with hardware. So that means you can have a logical AND or OR function just by using a relay, an electromechanical device. People later thought, having so many könnten Sie bitte Ihr Mikrofon ausmachen? Okay, let's go ahead. Now we have this safeguarding using software. And in case of the TERAC 25, which had a much higher acceleration voltage, which is 25 million of volts, so that means it's a very hard radiation. That was controlled with a PDP-11 process computer, which is a 16-bit computer, which was very, very popular at that time. In fact, I learned programming on such a computer. And now what happened is that some people were overdosed with such radiation, and the strange thing is nobody really noticed because some patients died, some came back, but the clinic said, okay, maybe it was an error on our side, let's keep quiet about it. But at one time it happened that in one hospital, a second patient was overdosed, And here, the doctor in charge, he did some experimenting. And he found out that under some circumstances, you can bring the machine in a mode that it's using the wrong radiation with much too high power, which means power which is a factor of 100 too high. And that means the patient has an overdose of 100, and that's not just dangerous, that's more or less deadly. And what was the reason? The reason is that the system had a computer, and on that computer screen you could set the individual parameters. But if the doctor or the personnel was hesitating and waiting a little, the computer jumped back one menu. And then when the menu was entered again, for instance, the system assumed that the attenuation aperture was set, but in fact it was not set. It was only indicated on the screen that it was set. And in that way, the doctor thought, okay, that attenuation is in action, but it was not. And in that way, the overdosing happened. And that doctor found out. And later on, the information was fed back to the company which provided this radiation system. And they said, no, that cannot be because our system has been tested. In the end, people found out that the software had been tested, but there had been never tests in the combination of the software with the hardware. And in fact, that phenomenon really only happened just by combination of software and hardware failure. So that system was not designed in a safe way, and that was the reason why some people lost their lives and their health. And that is one of the famous cases where it was shown that it is very important to make safe software. But now in this lecture, we will have several aspects of software. Normally, you could also say, yes, I regard software in the way that really the logical action in our system is safe. In that case, for instance, you must resort to some Markov graph or some similar method in order to verify that the system can only come into safe states. On the other hand, you would also like to know how probable is it that there is just one failure of the system by our software? And the question is, can software be treated like a failing element of hardware? And now let's have some data. Quite some time ago, some investigation was made, and it was also published in an IEEE journal, and that said, okay, if we have normal software, not for, let's say, really safety applications, you will typically have 25 errors for 1,000 lines of software. If it's important software, maybe it's only 3 to 2 errors in 1,000 lines. And when you have medical software, you have 0.2 errors in 1,000 lines. In the meantime, it is possibly much better. And the space shuttle, for instance, it had a software where they claimed it has only 1 error in 10,000 lines. Okay, What does that mean? So something is wrong. What does such an error mean? For instance, that means it can happen that you have a division by 0. In former times, when you had a computer with division by 0, the program was faulty, so there was a crash of your software, for instance. Of course, modern software is able to deal with this, but again, if you have a division by 0, some value you would like to know is wrong. Okay, now let's have a description. We have 1 to 25 errors after software has been cleared by the manufacturer, and it can even be up to 150 errors in a test phase. So possibly you heard about so-called beta version of software. That means more or less the software has not been thoroughly tested, but it has many more errors than software which you can sell. Okay, if you have an error portion of up to 25 per 1,000 lines, for instance, you can make an assumption about the fraction of fatal errors. So fatal means the system, or at least the software, will crash. So that could be 10%. And if you have some software, in fact, you must, at that time, people were using mainframes. That investigation was not aiming at personal computers. So you have possibly 10 minutes when your mainframe boots after a fatal error. Okay, so typically you can detect in that way errors, let's say 2 errors in 10,000 lines per year. And we have a large program. Again, now programs are much bigger, of 250,000 lines. Here we would have a total of over 5,000 errors. And in the first year, we would just detect 1,135 errors. Of these errors, we have 114 failures in the first year. And that means the first year has 8,760 hours. You divide it by 114. Then you have a mean time between failures of 77 hours. Okay. Now compute a fit rate for this. What is it? It is 13 million fit you have as a fit rate. That's extremely high. When you compute the availability, you take this mean time between failures. You divide it by mean time between failures plus mean time to repair, which is the 10 minutes. And then you get an availability of 99.8%. That sounds good, but in fact it is not, because every 3 days you have a computer crash, and a computer will just work for an average time of 3 days, and then it will crash again. So that means taking such assumptions and assuming that such an error is just appearing by chance. So you would assume an exponential distribution of errors or of error times. Then you can try to treat software like failing hardware, and you can assign it a failure rate. On the other hand, you can also think about some some failure function, and the probability for a failure when you call up a program or when you call up a subroutine or something is p. P would be a small value, let's say a promille or so, and the probability of having no failure is 1 minus this probability, so it is lower than 1. And then you can say the probability of failure, that is f of t, is 1 minus p to the power of k. And k is how often you call up this program, for instance, that subroutine. On the other hand, if you have a computer of a certain speed, you could say, okay, you have a rate of calling up that. The faster the computer, the more often you call this up. So you could say this rate of operation times the time here is replacing the k, and so the f of t is 1 minus p to the power of ht. And so that's f of t. And how do you get the failure rate, lambda? And as we say, it is defined, lambda of t is f of t divided by r of t, or divided by 1 minus f of t. And that is, on the other hand, 1 divided by r of t times the r of t derived by dt. So that's a change of reliability, or the change of, there should be a minus here, reliability per time. And that you can just put in here. So r of t is 1 minus. And if you derive this r of t, then you can say it is the logarithm of 1 minus p times 1 minus p to the power of ht. And you have derived this again, so you get minus a, and divided by 1 minus p to the power of ht. And so you get, it is minus h, that is the rate of call-up of your critical program, times logarithm of 1 minus p. And that means that's a constant that is independent of time. And that means under such assumption you can say software could behave in an arbitrary way, and you can describe the failure of software by an exponential function. Okay, and in that way we can describe the software behavior. So I would like to skip a little. What we can also say is the situation is not as bad when we take the lambda over time here. We can say we can modify our software. So that is what Microsoft is doing, for instance. You even don't notice it, but when the software has a failure, the information is fed back, and they will work on the software and improve it. And that's a reason why you get software updates all of the time, whether you want them or not, but that's state of the art. And that means in that way the failure rate is gradually decreased until you have a very new software, and then again you start with a high failure rate of your software. So that means you have a continuous improvement of the software, and but it is necessary to have a feedback from the user. So you must know when something is wrong. You also must know what was wrong, so you can improve it, and in that way all of the hidden errors are removed from the software. What is important here, in some way you can try to assume a behavior of the software like a failing hardware element. Okay, there are more models where you can compute in such cases the reliability function. I will not go into these details because I have other aspects to show you. First of all, I would like to point out that there were many reasons which were used in order to declare why software is better. And one of these is computers are cheaper than analog or electromechanical technology. So let's assume we have a telecommunication system and it is very complex hardware, and now we build it 10,000 times, so we have to pay for it, for the hardware 10,000 times. On the other hand, we can make a more simple system, maybe just one microcontroller and software. Repeating the software will cost you not much, and in that way you can assume that computers are cheaper than analog or electromechanical technology. Something which is in combination with this is software can be modified easily. Of course you can do it. You can just go into the source code and change something. Okay, it can be done easily, but the question is it done in a competent way? To give you an example, the fraud software in the diesel engines, could you just set it back? I think it could be set back easily, so the exhaust gases are cleaned more thoroughly in normal operation. I don't think the effort would be high, but the consequence for the car could be severe. In fact, it could happen that cars fail prematurely, and in that way it can be modified easily, but the consequence is still open. Computers guarantee a higher reliability than the system which they replace because software cannot fail. It doesn't fail in a way hardware fails, but it can have errors because software has hidden errors in it, and at some point of time or under some circumstances this error will appear and lead to a fault or even a failure. Improvement of software reliability will automatically improve the system's safety? Of course not. For instance, for this radiation therapy machine, it would, let's say, it would have no consequence if the software has a mean time between failures of 1,000 hours or 10,000 hours or 100 hours. The logic of that software was wrong, yes? And in that way, you cannot just say how probable it is that the software will fail, but also how the complete, let's say, chain of actions is affected in that system. And that's the reason why we have different methods. We can compute a failure rate by parts count method, for instance, and on the other hand, we can use Markov processes to investigate chains of action. Correct testing or verification of software can eliminate all failures. The question is all. Of course, it cannot eliminate all failures. More testing will eliminate more failures, but you also need a proper strategy. Reuse of software will improve safety. Here you can say no, no, no. Maybe the failure rate of the software will be better, but the safety will not be, because software must always be tested in the proper environment. Yeah. Computers will reduce the risk compared to mechanical systems. Again, you can say, do it correctly and discuss these statements. Maybe it would be a good idea to find for each of these statements a counter argument, especially one which is based on some technical consideration. Okay, and now taking that into account, we talk about design, simulation, and test of mechatronic control. So let's say the following. What is mechatronic control? In former times, a car had a carburetor, and there was some rod from your foot pedal to the carburetor, and the throttle was opened just in a mechanical way. So the carburetor got more air, and the motor was sucking in more air and also more fuel. Okay, that was just a mechanical system. Now times have changed. We have a system that measures how much air goes into the engine, and very precisely the fuel is added in order to have a so-called lambda ratio, which means we will not pollute the air by unburned hydrocarbons, and in that way also the catalysator can operate properly. Okay, for that reason we need some electronic control unit. For instance, it is plugged in here. Here we see it also with some cooling fins on top. That here has no cooling fins, but it controls how an engine is working. On the other hand, that's not really some safety feature, because, okay, an engine can fail, and in most cases the situation will not be too dangerous. There are other electronic control units where failure would be more dangerous. Imagine, for instance, the braking. When you lose a braking function, the result will be you can crash into some structure, and that could be deadly. Okay. Also, what is important is, for instance, a steer-by-wire system. Now, let's have a look how it would work. So we have some gear, and that gear is operated, and in former times you were rotating the steering rod, and it was directly coupled with the gear, and in that way the direction of your wheels was changed. Now in steer-by-wire we have a motor which changes the direction of the wheels. But on the other hand, what do you also need? You need something which tells you what the position of your steering, of your wheels is, and also what the position, of course, of your steering wheel is. Because there can always be a small offset, and that offset adds up. And in order to avoid this, you must always have a well-defined zero position, for instance. Okay, that's not all, because when you do steering in a normal mechanical car, and you are on normal ground and driving slow, you have relatively high forces you need. If you are on ice, the forces of moving the wheels is very low. So the force you need for steering gives you very important information as a driver. So an experienced driver will be able to feel how the state of the road is. Is it slippy? Will it have a good grip or so? And in that way, it is important to have the feedback. And now we see we have very many systems, and when we want to do it in a mechatronic way, we need both. We need hardware, which will not fail, and we will have software, because we have several control and measurement circuits here. In fact, such a system is much more complex than the initial system with a steering rod. And so it must have many or just important advantages. For instance, an advantage here could be that you can steer the wheels individually. Of course, then you need more steering motors, but that is one of the possibility you have here. So you need sensors, you have the control, you have actuators, but now when you want to make such a system safe, you have a general aim. That's to avoid dangerous errors, you avoid faults, and you avoid failures. Another thing which is important is optimize the control behavior of mechatronic systems. For instance, that means the system is reactive or not, yes? So you can also have this in a mechanical system. For instance, you can have power steering, and that power steering can give you very low forces, or you have no power steering, then you have higher forces on your steering wheel. The reaction time, how fast the system reacts to your wishes or to your commands. If it is really a controller, it could be a PID characteristic, proportional integral differential, and all of this must be optimized. So the tasks are to find optimum algorithms and control parameters and convert them into software. And here, again, I must say we are not longer stuck with reliability, but that's really safety and the behavior of, and the functional behavior of systems. There are other things which are important. For instance, imagine we want to introduce steer-by-wire, and we want to bring steer-by-wire into series. And what is often important is the control software, because it defines the functionality. And you want to test that software, while on the other hand, the new car which uses steer-by-wire is not yet built. And that's the first thing. The second is, maybe you build a car you want to test the software in combination with hardware in a car, while on the other hand, the hardware system of the computer, for instance, does not yet exist. And also, when you already have the series target hardware-software system, you want to verify its functions, and you want to verify it without driving. Why? Driving is taking a large effort, and on the other hand, if you do something like steer-by-wire and you do experiments with it, it's also a safety issue for the test driver, because you cannot endanger him. So in fact, you would like to test the series target hardware-software system to verify its function. And in that way, you want to test and analyze a system systematically under well-controlled conditions and in situations that cannot be reproduced reasonably or safely. As I said, you do not want to endanger a test driver. And finally, you want to optimize the series system. That is important because when you look at mechatronic development, you have mainly three things. You have the hardware, for instance, the hardware of the car. That's more mechanical engineering. Then you have the software. The software is more a part in the electronics. And for the electronics, you also must investigate, for instance, assembly and packaging. So we have the electronics, we have the software, and we have the mechanical part. And in that way, all three are designed in different ways. You can say normally mechanical hardware is designed by mechanical engineers. They have CAD tools for mechanical engineers. They have finite element methods for mechanical engineers. Software is sometimes developed by computer science people, but it is also often developed by electrical engineers. But they have different tools compared to the people doing the mechanical part, and the electronics, including the assembly and packaging, they have still other tools, and also they have special tests, for instance, temperature cycling and so on. And in that way, we have three lines which are more or less independent, and in the end, all of these must be united. So that means the complete development is very complicated. In all three areas, we must have risk assessment. For instance, we do FMEA, we do fault tree analysis. What we also do is electromagnetic control. We will not treat it here. Quality function deployment, that's some method in order to optimize quality. We do lots of simulation. We have version administration. That means we optimize our system, and from version to version we must make a documentation. Also, what I noticed from time to time, when there is no good version administration, maybe in some optimization you suddenly use a wrong older version, that's also not so good, and brings in errors and faults which you had eliminated, and so on. So there are many techniques you must employ here. Generally, the idea is you use the V model of specification and of building. So when you have, for instance, a mechatronic system, you do a specification, you do a coarse design, you do a fine design, you specify the modules. That's software here. And then, for instance, you would like to do a modeling of your software, so you must create the software. And what you also would like to do is you would like to do some offline simulation. Offline simulation is often performed in some simulator. For instance, MATLAB Simulink is such a method. And in that way, you can already develop, for instance, a control algorithm or a controller and so on. And here you can already investigate the functionality. So here you can define the dynamic behavior. You have an early verification that is necessary, and you can do it in a preliminary way, but just using software. What you can do then is you can take that software and transfer it to a special code, and that code is for some universal ECU. So that is not the electronic control unit, which will finally be in a Volkswagen or a Mercedes, but it's a special computer where you can upload the software you have defined, and that computer can be built into a test car, for instance. And in that way, you can test the software on a module. Yeah, and what is important here, you had this coarse and fine design, and you must upload it to that rapid control prototyping ECU, and that can be already done in an automated way. So what you get then is you have the software for a controller, which exists as a hardware, but which is not the target controller of your car. It's just a controller that emulates this behavior. And starting from this, you can proceed, but first of all, it's important to transfer the software from MATLAB, which is here, or some other software, to the machine code you have here. And if you have already produced the other parts of your, let's say, steer-by-wire system, then you can already build up such a system in a test car, and you can start and you can try how it behaves when you do some driving. Okay, that's for today. For today, we are not finished with this part. I will proceed with this in the next year, but for today, I'm thanking for your attention. See you.